Today we're talking about friction. And so here we go. I have a book sitting on a table. All right. Now we understand that that book has a certain amount of friction between it and the table. It's very intuitive, right? I have to push on the book a little bit more than what I would think I'd have to get it going. And so why is that book sticky to the table, right? Well, really it comes down to the microscopic geography between the two surfaces. And so the intermolecular forces of the table pushing on the book and the intermolecular forces of the book pushing on the table are due to atoms. Atoms are different shapes, sizes, spacing, etc. That creates kind of a topography or geography of the material. And you can have all sorts of different geographies here. There's some advances in material science. There's a thing called graphene, which is a single layer of carbon atoms, and that forms a near frictionless surface. Obviously a book and a table are not near frictionless, and so there's some kind of jaggedness to the material, and friction is the relationship between that. So this is mu. This is called the coefficient of friction, and this relates the two materials, any two materials. So this coefficient of friction is testable, and it's known between certain materials. It is based on the force of the friction divided by the normal force. So if we rewrite this, the force of friction is equal to mu times the normal force. We could say that friction is dependent upon, sometimes the normal force is referred to as contact pressure. In this situation right here, the weight is equal to the normal force, and so for most things, and the normal force is often equal to the weight, and you could see if I increase the weight, I would increase the normal force, and I could actually push down on the book. If I added an applied force, then I would essentially be increasing the normal force, and so that's contact pressure. This is friction in a nutshell. There's a few types of friction. We'll go ahead and cover those. Static friction is the force when an object is at rest. And so the idea is that those jagged molecule structures on each object have time to sink into each other and really align. And so the static friction is going to be greater than the kinetic friction. After that object kind of breaks free of those deep troughs of the molecular structure and it moves, it's just going to hit the wave tops, and so there's still friction there, but it's much less than static friction. You can solve for the coefficient of static friction by looking at the angle of slip. So this angle right here is theta. It's theta slip, or the angle of slip. When I solve for the coefficient of static friction, I'm going to have to change this angle. All right, remember that this is going to be 90 minus theta prime. So I'm going to use theta prime here. So that I can keep all my math the same. So this is f of g of x. And then I'm going to go ahead and do my net force in the x and the y and see if I can solve for mu. And I'm going to substitute this over here. And so that's going to give me, my forces cancel out here, my weight cancels out. Cosine over sine is 1 over, and I want to express my answer in terms of the angle of inclination, and this is not, right? That was up here. That's just kind of how I memorized this math. I think it's beneficial to just keep all of your y's with sine and all your x's and cosine and make things a little bit quicker, because this 90 minus theta is so simple, okay? Well, if I take the complementary angle here, what I can really say in terms of angle of slip, or this angle of inclination, is this, the mu of static friction, or the coefficient of static friction, is equal to the tangent of theta, where theta is the angle of slip. And so I can solve for the coefficient that's very specific between two materials by putting it on a plane and raising it or lowering it until it breaks free and starts moving. Okay, so that is the coefficient of static friction. Kinetic friction. So kinetic friction is less than static friction. And so if I change this with my subscripts K, I understand that this object has some velocity larger than 0. Okay, it's sliding down the hill. It's sliding down the hill because f of g of x is pulling it down the hill. So a portion of the weight is sliding it down the hill. You would use the coefficient of kinetic friction, and you would solve this like any other force. Okay. So if I wanted to know the acceleration, I would do the summation of the forces in the x dimension, and you just work it like any other problem, and you'd be able to plug in your coefficient of friction. It is important to note that the force of kinetic friction is always going to be opposite of the direction of motion. So this is an object rolling. So I have a pool ball sitting on a flat surface, and I would give it kind of an initial push, right? And then after I gave it my initial applied force, I let go of it and just let it roll. Okay, this is an unbalanced force. It would eventually come to a stop. We've experienced this before. The reason it comes to a stop is because of friction. Now this is not a brick, it's not something sliding on a table, but it has some velocity that's greater than 0. It has a weight, and it has a normal force, and there's a rotational piece to this. So it's weird to think about. This object could actually have two different types of friction depending on how it's behaving. And so again, this is where the physics comes in. It's like you have to apply the correct physics to the problem. If the ball is rolling like this, then the point at which it touches the table doesn't really matter. Okay, it's causing a rolling friction, and that has a coefficient of its own times normal force, just like all the other friction problems. Okay, now maybe you can translate this to your car. Okay, your wheels typically roll, right? You're probably going to experience this in the wintertime, and as your car is rolling and you're gently applying your brakes over slick surfaces, your car will continue to roll and it will behave normally. Okay, and you can expect to experience a rolling friction. However, if you slam on your brakes and it's a little bit slippery out there, your brakes lock up your wheels, and now it's no longer a rolling object. You now have rubber and pavement, and you have a kinetic friction scenario. Okay, and then you could take this analogy one step further. If I parked my car on a hill, now I'm looking at the static friction. And so depending on how the object is behaving, you need to apply the correct friction component to it. And this is a typical free body diagram of a rolling object. Drag, there's two different versions. You've got microscopic drag and macroscopic. Microscopic, I'm talking about a spore or a particle of dust or something like that, right? Floating through the air, floating through the water. And then macroscopic, I'm talking about, baseballs and birds. So when we talk about a fluid, this could be a gas or a liquid. So usually it's the air or it's the water. Now, when you're talking about air and water, temperature has a huge influence on how dense the molecules are packed together, how much they're vibrating, how much they're going to get into the way of an object trying to move through it. Okay? And so all of that is dependent upon this variable B. And so for microscopic objects, F of drag is equal to BV, where B is a constant. This could be altitude dependent, temperature dependent, molecule size dependent. It really depends on what it is you're talking about. The state of the fluid, it could be a gas or a liquid. This constant is going to be different given all those different criteria. It's very similar to mu when it comes to static, kinetic, and rolling friction. Is it based on the materials? Well, this is going to be based on the fluid. And then V is your velocity. So it's interesting that drag is based on how fast you are going through it, right? A few different materials that you encounter are based on the velocity of something going through there. You can think of like ballistic glass or Kevlar or something like that, right? Kevlar won't stop a slow knife moving through it, but it'll stop a high velocity bullet. Same thing, water. Okay, I can move pretty easily to the bottom of a pool because I swim very slowly, but if I were to shoot a bullet into a pool, it's only going to go a couple inches, or sorry, a couple feet. And so before this B value takes over and stops it. So fluids are very interesting. Macroscopic is going to be a little bit different, and so you have a larger effect on the velocity. So F drag is the constant times the velocity squared. So this affects your object much more than just a microscopic object. So this is drag. Drag has some implications of its own. Alright, I've got a typical vertical launch, and often I use V equals 0 at the top to do the delta Y max, and that happens at T half. And the reason we can say that is because we approach a projectile motion with the idea that the up is equal to the down. Okay? If we take air resistance into consideration, then that's not quite true. So drag will affect the object on the way up, and it will affect the object on the way down. So if I take an object somewhere along this curve, I know I've got weight, but I also have drag, because drag is going to be opposite of the direction of motion. So if my object is moving this way, then I've got drag going down. And so for simplicity, we're just going to say everything's in the y dimension, straight up, straight down. And we're not going to look at the angle of this. Okay? And so as I go up, I have two forces pulling down. So let's look at what that means. So the net force on the way up is equal to negative F of G, and I have negative drag. And just to put some numbers in here so we can compare both sides easier, I'm going to say that the weight of this object is 10 and the drag here is 0.5. And so that gives me, 10.5 newtons down. Okay? It's a negative value, and that negative value is going to end up causing my object to stop, right? The max velocity is down here at launch, and it gets slower and slower and slower. It's decelerating until it comes to 0. Okay? If I look at the net forces down, 9.5 newtons. So if we kind of take away the minus signs, just think about what's happening here. I know this is speeding up, and I'm using a net force smaller than my net force going up. So what's happening here is this thing's actually slowing down faster than it's speeding up, right? And that makes sense because both of these forces are causing it to slow down. And then over here, I only have one force trying to speed it up, and I'm actually fighting this drag. Okay, so here the object as it moves up, it's fighting drag and the weight, and so it's going to slow down quicker. Here it's only fighting drag. Okay, so the effect is not symmetrical. So I think that's it for friction and drag. It's important to understand which friction to apply, and then after that it's just like a regular free body diagram problem. Here's your friction for you, and good luck. Thanks.